Welcome to yet another exciting educational video brought to you by Christolite Tutors. Today we'll be looking at MTH 112 from the National Open University Scheme. Topic for discussion today is higher derivatives and implicit functions. So as a way of learning objective, by the end of this class, you should be able to compute second and higher order derivative, interpret higher derivative in practical and physical situations, differentiate implicit relationships, whether y is mixed with x, where y is with x, and apply implicit differentiation to curves like circles, ellipses, rational curves, and trigonometric constants. Handle real examples and short assessment exercises confidently. So sit tight. If you're here to subscribe to our channel, kindly go to the subscribe button and subscribe to Christolite Tutors for more exciting educational videos on the STEMs. Also share and engage us in the comment section. So we'll dive in. So when we say higher order derivative, what do we mean? Higher order derivatives. What do we mean? You know, we have known how to differentiate in first order. So first order means differentiating once. For instance, first order derivative, first order is, I say dy dx, or I would say dy then dx, or I can say y prime. Understand? Y prime. So that is differentiating the first time. But higher order derivative have to do with second order, third order, and fourth order. What that means simply is that for second order, I will just differentiate derivative of the first order. So for second order, I have the instruction or the 2y over dx power raised to power 2. Or I have d, okay, let me use y prime prime. So this 2 prime here is showing me that it is the second order derivative. Or if I have the 2y over dx squared, so that is a second order derivative. So you can call it second order derivative. So the third order is differentiate again second order. So I have the 3y over the x cube, or y prime prime prime, right? Then okay, I can put this one like this, or the 2y dx square, or the 3 dx cube of y. It's the same thing. Fourth order is differentiating again. The third order, whatever you have in third order, you differentiate it again. So the power shows the order. The power shows the order. And the number of primes shows the order as well. So this is how it's being done. So there are useful tips in physics. So let's go into exponential function. So if I have y is equals to exponential 3x, okay? So first derivative, y prime, is this 3. This 3 is the coefficient of x here, right? So 3 times 1 is 3, exponential 3x. Again, y prime prime, that's second order. derivative is equals to this 3, coefficient of x is 3, times this coefficient again 3. 3 times 3 is 9, exponential 3x. Okay? Now, the third order, 1, 2, 3, is 3 times 9 is 27, exponential 3x, and so on, and so on. So the order of derivative is you differentiate the expression of the previous order. Okay, so the first order is always the first differentiation. Second order is differentiate the expression for the first derivative. Third order is differentiate the expression for the second order derivative. All right, so let's go into implicit differentiation. Okay, so some equations define y in terms of x without explicitly solving for y. For example, if I have function of a circle, the function is x squared plus y squared maybe is equals to r squared. So r is the radius, or let me just put a value there, 25. Understand? 25. So this is a circle. This is an implicit function. Why? Because y is inside the expression. Okay. So an ellipse is also another. An ellipse. Ellipse is expressed as x squared over y plus y squared over 4. Okay. Okay, let me put this y as 9, sorry. Because it's a constant term that will be there. It's equals to, let me say 1. So you see that in this expression, you have x and y inside of it. You understand? It's not explicit. Explicit is when I say y is equals to mx plus c. Y is a function of x. So y is explicitly expressed as a function of what is inside here. You understand? But implicit function is that y is even part of the function. Okay, I know you understand what I'm trying to say. Now, a rational relation, a rational relation like this, when you have x, y plus x is equals to 12. So these are the functions that characterize or that explains what implicit function is. Okay, so to differentiate implicit function, what you need to do is to treat y as a function of x and apply the chain rule wherever you differentiate y. So for this one now, if you see x, for instance, you treat y as a function of x, so you differentiate this one normally, understand? But for this one now, you are going to differentiate, take y, differentiate this one, but also multiply by y. You understand? You treat y as a chain rule. That's apply a chain rule when you are doing y, because y is implicit. Okay, so we're going to quickly dive into this thing. So what I'm saying now, the key rule for this kind of differentiation, for implicit differentiation, is that you say the ddx of this function is equals to, that is of y, if y is inside here, to differentiate it is equals to this n will come n, then I have y, then n minus y. That means n minus 1. That means I have differentiated y as if y is a function of another thing. You understand? But at the same time, I'm treating it as a chain rule. I will now also put a dy dx. So this is the general form for implicit function. That is how you will treat y inside an expression. If you are differentiating, normally you differentiate x normally. When it comes to y, you will differentiate it using this pattern. Let's say I want to solve this one, for instance. So what I will do is I will differentiate this first term, 2x, sorry, x squared, as 2x. Why? Because this power multiplied this coefficient, and this power at the same time reduced by 1. That's why I have it as 2x. But when it comes to y squared, I will use this formula or this expression here. I will say this 2 power comes down, it's going to be 2y, then this same 2 reduced by 1, that's 1. Then I will now say dy dx is equals to 25 is 0. So this is the first differentiation, understand? But I'm not done. I've just applied this thing to where I see y. So I'll continue. I will say that I will make this one to the formula, dy dx to the formula. So I have 2x plus 2y dy dx is equals to 0. So 2y dy dx stays in one side, 2y dy dx is equals to 0, then minus 2x. Again, 2y dy dx is equals to minus 2x. Then I will now divide both sides by 2y. So dy dx is equals to minus 2x over 2y. It can cancel, right? So dy dx is equals to minus x over y. This is just a snippet of what we're going to be seeing under this particular subtopic, differentiation of, that's implicit differentiation. Okay. So still under implicit differentiation, we are going to implicit rational equation. If I have this kind of equation, xy plus x is equals to 12, and I'm asked to differentiate 10 by 10. So I'm going to differentiate this one using product rule, remember product rule, and differentiate this one normal differentiation and get my answer. So for this term now, to differentiate, I'll use product rule. I will say, in the product rule it says this did this plus this did this, right? Remember, this, when I say this, I write this one down. When I say did this, I'll differentiate this. Then plus, when I say this, I write this one down, and did this, I'll differentiate this. Just follow me. Follow me. If you are confused, check out my video on product differentiation in my playlist of this particular series. So this is like a product because it is x and y. They are both functions. They are both functions. So I'll say this. When I say this, I write it down. Then the this is dy dx, right? Then plus, then this, I write this one down. Then the this is 1. Okay? Then plus, differentiate this one, I have 1. Is equals to, differentiate this one, I have 0. So I have done my first line. So what I will do again, I will just make it simpler. I will say x dy dx plus y plus 1 is equals to 0. Is equals to 0. So I will have to make this one is the subject of formula. Subject of formula. So I will say x dy dx is equals to minus y minus 1. So I can now divide both sides by x. So dy dx standing alone now is equals to minus y minus 1 all over x. Or it can be minus y plus 1 all over x. That is the dy dx. That is of this function. Okay. Okay, so now I have on the board, this is a trigonometric implicit example. So when you see here implicit, it means x and y are mixed inside the expressions. But I told you to always treat them as a chain rule when you were differentiating the y aspect. All right, so we're going to differentiate it. First of all, there's a left-hand side. This is the left-hand side of the equation, and it's a right-hand side of the equal sign, right? Now, for the left-hand side, I see that this is a trigonometric function. It's implicit, right? Okay, so we're going to treat this one as function of function. There's a function inside of function. All right, so that function inside, I would you differentiate it and differentiate the brother function. The brother function differential, that is, if you differentiate this one, sine is already cos. So if you differentiate sine, it will be cos. So it's cos x plus y differentiated, right? But because we are doing a function of function, you also differentiate this one inside. Differentiate this one inside. What you have is, differentiate x, you have 1, yes. Then differentiate y, again you have dy dx. So this one is a function of function. Function of function. Then for this one, it's a product rule. There are two functions here that we see them as two functions, but they multiply themselves. So again, for product through differentiation is this did this plus this did this. Again, I'll write it down. This, I've written it down, right? Then this is dy dx. Okay, plus this, all right, y, then this is 1, right? Okay, so at this point, I will just simplify. I will simplify, put them together. Okay, so my target is to make some sort of formula, right? Okay, so what I will do again is to look for how to multiply this across. Okay, you see, you have dy dx here and dy dx here. So use this one to multiply into this bracket. So I have cos x plus y times 1. So I have cos x plus y. This one times 1. Then this one again times dy dx plus cos x plus y. Then dy dx, right? Is equals to, then I have x dy dx plus y. All right. So I have this term and this term having dy dx. I can move them to one side and move them to the other side. So this one, I'll write it out as cos, open bracket, x plus y, then close it, then dy dx. That's this term. Then I'll take this one to go and join it. Why? Because this one and this one are having the same term, dy dx. So minus x dy dx. Then I put my equal sign. Then I will now write this one down that is remaining here, which is y. Then I'll take this one to go and join it there. So we minus cos x plus y. Okay, so it's looking better now. So I can now factorize. This common factor is dy dx, right? So I'll put dy dx outside, then open big bracket, then I'll put cos x plus y, minus x, then close the brackets, then equals to y minus cos x plus y. Okay, so at this point, I can now take my dy dx as the subject. Dy dx is equals to, then I write this one, y minus cos x plus y, then all over cos x plus y minus x. So what I did was that I just divided this by this to give me this expression. Note that the minus sign here is not affecting this one inside because it's a trigonometric function, right? And so this is the answer for this particular differentiation. That's the answer for this particular one. This is the question. Question, answer. All right. Okay, so in this section, we'll be looking at implicit differentiation combined with chain rule. So all earlier rules stay in play while we are doing this. But every time you encounter y, just multiply by the x, dy dx, after differentiating. Okay, now we are going to be using, doing this example. Let's say differentiate y cubed plus exponential ex exponential xy is equals to 10, right? Now look at this kind of function. We're going to be using both chain rule and implicit function. Chain rule says that this is this and this, they are like both functions. You understand? This is a chain rule again. Then this is implicit, right? You have y inside. You have y inside here, right? Equals to 10. So each of the 10, we're going to treat them, differentiate them. When we see where we have y, we'll treat them by using both chain and implicit function. Now to differentiate this first one, this first term here, I will just differentiate this one as the normal function. You understand? So this is 3 times 1 is 3y raised to the power 2, right? But because there is an implicit function of y, I'll put dy dx. So this is the differential of this. But for this one, exponential xy, right? So we're going to do using chain rule. So in chain rule, you have the outside derivative and the inside derivative. Now the outside derivative is, remember, when we say exponential 2x, for instance, so we say let u is equals to 2x and y is equals to exponential u, right? Then I will now say du dx, okay, dy dx is equals to du dx dot dy du, right? Remember this play. Okay, now for this one now, you see that there is the inside function. The inside function is this one, this first one here. So this one is the inside function, right? Then the outside function is this one. So this outside function, if I differentiate it, for instance, because I'm multiplying both inside derivative and outside derivative. Okay, let me explain very well. Recall. If I have y is equals to exponential 2x, for instance, right? For chain differentiation, I say let u is equals to 2x, right? And y is equals to exponential u. Therefore, dy dx is equals to du dx dot dy du, right? So this du dx, this u here is the inside function, and this y here is the outside function. So for this particular one, inside function is this one, right? I'm going to differentiate this one. Then outside function is the whole of this. Now, if I differentiate outside function, it's the same thing as saying exponential ex. It does not change. But the inside function, this one, is going to be a product rule and implicit function together, because they are product of two functions here. So I will just say times, maybe that times I'll open a bracket because it's going to be some product of sum of two terms. So I will now open my bracket. I will now say this x dy dx plus this y, then dy dx here is 1, right? Okay, so that's it. It's equals to 0. So differentiate 10, I will get 0. So I'm going to continue from here. So I will have 3x squared dy dx plus exponential xy, open bracket, x dy dx plus y is equals to 0. Now, I'm interested in this dy dx, this term and this term. So I'll open this bracket up. So I say 3y squared dy dx, opening this one, plus exponential xy times this, I'll get exponential xy dot x dy dx plus this times exponential xy dot y is equals to 0. So I have these two terms. I can factorize. This one will go to this side and factorize this side. So this one is, they are common, right? They are common. So I'll say dy dx, right? The remaining one, I have 3y squared plus this one is exponential xy dot x. Or I can say x, this one x outside, this x is outside, dot exponential xy, right? Then I close it. So this one can give me these first two terms again, because I'll say dy dx times 3y squared will give me this one, and dy dx times this one will give me this one, right? So I didn't change much. So for this one now, I will now say it's equals to 0, then minus exponential xy dot y, or minus y outside. Yes, so this is how it is. So from here now, I will make dy dx sort of formula. I will now make a sort of formula, and I will now say dy dx is equals to minus, this 0 can go out, minus y exponential xy all over 3y squared plus x exponential xy. So this is the answer for that differentiation. So you need to know how to apply the rules. So this is actually an implicit function. Why? Because we have y inside the expression. This one can be differentiated normally by just differentiating this one and bringing out one of the derivative. That is just, this is the derivative of this. You know, general form, like I said earlier, for higher order derivative is you have recall I said the higher order derivative is n y n minus 1 dy dx, right? That's what we applied here. Okay, so then for this one is a chain rule, function of function. There's a function, this bigger function has a smaller function inside. So the way to do this one is that you have the inside function and the outside function. Get the derivative of the inside function and outside function and multiply. That's what happens when you see something like this. So the inside function is what is here, and the outside function is this one. So when I differentiate the outside function, I just imagine that this one is a particular term, maybe a particular term. So exponential x is the same thing as exponential x. That's why this one, the way it is, it came here, outside function. But the inside function is where you now use the implicit function, but it's a product. You see, so there's product combined with implicit, so it's a product. So I'll now come and say this did this. So this is x. I put x. When I say this, you just put it. Then this means differentiate this one. Understand? Plus, then you reverse it again. This one, you write it. Then this, you differentiate that. So that's how that one came about. From here on is simplification. All right. So it's actually an interesting topic. And requires constant practice. So I'm going to be leaving some questions in the comment section for us to work on, and also check your materials, the TMA questions. You can give us a feedback. If there are questions that you can't solve, you can put them in the comment section or send an email to us. So I hope this video has been useful for you. I'd like to thank you for viewing.